Hey Elixir friends, welcome back to this video series where we explore network programming in Elixir by solving the challenges on protohackers.com. If you're new here, and especially if you want to follow along, you might want to start from day 0 over here, which is where we set things up and we give a bit more context and then work through the other videos. In this particular video, we'll deal with our first binary protocol. We'll parse some binaries by using Elixir and Erlang's excellent support for that. And then we'll just generally have fun. It's going to be a little bit shorter because the problem is a little bit shorter, but yeah, let's get started. Okay, so this time the problem description is pretty straightforward. Essentially, we'll be building a TCP server that can respond to two kinds of requests, which are insert requests, which insert a timestamped price in our database, and query requests, which ask for the average price in a given time interval. So we'll be building a sort of small, simple database. The problem specification details the binary protocols here. And the binary protocol is made of a single byte that specifies the kind of request. So it's going to be capital I for insert requests, and then it's going to be capital Q over here for query requests. And then there are two big endian 4-byte integers following that, and their meaning depends on the request. So for insert requests, the protocol specification is here. For insert requests, the first byte is I, as we said, and then the second 4-byte integer is the timestamp in seconds since January 1st, 1970, so it's a Unix timestamp. And the second int 32 here is a price in pennies, and then there are some notes that say insertions may occur out of order. All right, while rare prices can go negative, so we can have negative prices here, and behavior is undefined if there are multiple prices with the same timestamp from the same client. So this kind of frees up data structure choices basically. And then the query message, instead you have the Q as the first byte to tell you it's a query message, and then the two integers here represent the boundaries of the range of timestamps that we want to query. Responses are made of a single, they're detailed here, and they're made of a single 4-byte integer, and the integer represents the average of prices within the requested range. So now we know what to build. There's an example session over here with bytes and everything. 5 simultaneous clients, and when a client triggers undefined behavior, the server can do anything it likes for that client. Also, somewhere in the beginning, it mentions that prices are kind of scoped per client. Each connection from a client is a separate session. There you go. Okay, so we know what to build. Let's build it. Okay, we're ready to go. So let's start again by, like last video, by copying over the initial echo server that we wrote for the first problem. So I'm going to do cp protohackers echo server, and I'll copy this into protohackers prices server.ex. Perfect. We will rename the module here to prices server. Perfect. And then we'll change the port to listen on port 5003. I'm just following essentially just consecutive ports. We used 5002 for the last problem. We're going to use 5003 for this one. Great. And let's add the module to the list of children that we're going to start with our application protohackers.prices server. Okay, and let's also add this to our list of children. It's going to be protohackers.prices server. Great. And if I run the application now, we'll see that yes, something is listening on port 5003. We're also going to change the name over here, starting prices server. Okay, great. So this time there's really just two things to work on. The first one is the binary protocol, and then the data structure that we'll use to hold the prices. So let's start from the data structure. Okay, so we want a data structure that will let us query lists of prices within a given range of timestamps. There's many ways we could implement that, but let's keep it simple. We'll just store prices in a list alongside their timestamp. So when getting a query request, we'll just filter out the timestamps outside of the requested range and calculate the average of the matching prices. This is not really efficient because we won't be taking advantage of the sorting that we could have. However, this is a series about networking, so I won't try to be too clever on the data structure side and optimizing for that. And just for funsies, we'll benchmark how well the solution performs later with a few 100,000 elements to make sure it's just not ridiculously slow, and we'll see. So let's have a separate module so that we'll be able to kind of test it out and encapsulate the data structure. So we'll isolate this functional layer. So to do that, I'm just going to create a new directory, which is going to be protohackers prices server. And then I'm going to create a file in there. So I'm going to say protohackers prices server slash, let's call it db. Okay. So let's open this out. And I am encapsulating the shape of the DB data structure in this module. Let's start with protohackers.pricesserver.db. Most often, I'll actually reach for a struct here, which gives me some sort of just lightweight typing where I can say, or is this DB, by checking if it's a struct. That's a DB struct, and it gives me like some fields that I can kind of check. But here the data structure is so simple that we'll just really go for a list. So I'll provide a new function that returns a new data structure, which is good because we could change it later. Just encapsulates creating this data structure, and then we'll provide an add function that takes a DB, it takes a timestamp, and it takes a price, and we will add this timestamp and the price to our DB. Since we'll filter this out and order won't really matter, we will just add at the beginning of the list, which is the quickest thing to do. But so it works for us. One thing that I also like to do is I like to say when is list DB and is integer timestamp and is integer price. So I really like to use guards. Again, it's some sort of like, make-believe type system at runtime, but it's better than not having it, I think. It makes the code a little bit more verbose, but it's so much better to check these things at the boundaries, right? So I usually don't add the guards to private functions. I only add them to public functions so that when stuff comes in a module, sort of, it's like it kind of has the right type, right? So this function is pretty straightforward. We're also going to have a query function, takes a DB, takes a from kind of timestamp, and then to. That's again when is list DB and is integer from and is integer to. And then what are we going to do? So we take our list. I'm going to stream.filter out all of the timestamps that are not in the range. So I can say timestamp greater than or equals to from and timestamp. So all the timestamps that are in the range. I'm using stream so that we don't compute this list right away, because then what I want to do is I also want to kind of say map that just mapping the price here, so we can work on a list of prices that already match. Okay, and then what I'm going to do, I'm going to calculate the average by reducing over this, starting with 0 elements and the sum being 0, and I do so price, and this is sum count, and I'm gonna say return sum plus price count plus 1. Okay, and then I'm gonna use the then function. So there's if this is gonna be an empty list, I still want to, if I filtered out all the elements, essentially there's no elements in this range, so I still get 0, 0 here. I'll just return 0, which is the problem definition. When there's no elements that match, the average is 0, because the average of 0 numbers otherwise doesn't make sense. And otherwise, if the sum and count are here, I can do integer division of sum divided by count. Also, I really don't care about this. The important thing is that I don't divide by 0, basically. Okay, so this should work. Let's write a test for this data structure. Oops, I have a syntax error here. Sorry. Okay, let's write a test for this data structure. I'm going to do kind of the same thing here, where I create test protohackers prices server as a directory, and then I say I'll create a file in there, and we'll call it dbtest.exs. I open this protohackers.pricesserver.db test, and I'm gonna alias protohackers.pricesserver.db and also use xunit.case. Great. And then I'm gonna say, I'm gonna test both functions at once. I'm gonna say adding elements and getting the average. I'm gonna start by saying db is a new db, and then I'm gonna assert that db.query db from 0 to 100 is 0 when there are no elements. Then I want to add a bunch of elements, so I'm going to say db equals db db.add, I don't know, 1 with it. So the first one is a timestamp, right? Like at timestamp 1 we'll have the price 10, then at timestamp 2 we'll have the price 20, at timestamp 3 we'll have the price 30. Okay, and now I do a bunch of querying. So if I query from 0 to 100, so essentially all of them, the average is going to be 20. Then if I query from 0 to 2, so excluding the third element, then the average is going to be 15. If I query from 2 to 3, like the second two elements, the average is going to be 25. And if I query an empty range, so like 4 to 100, then the average is going to be 0. If I run tests, okay, so they pass. So it looks like we got our data structure. Okay, so now let's do the silly benchmark that a non-scientific silly benchmark that I mentioned for checking if this data structure is ridiculously low. And what I'm going to do is I'm just going to test this out in IEX. Again, not scientific, but just to get an idea. What I will do, let's create a DB by reduce over 0 to 100,000, 500,000, I don't know, 500,000 elements. Protohackers dot prices server.db.new, and then I'm gonna get accumulator here, and I'm gonna add protohackers.prices server.add accumulator. Let's say the timestamp is I times 1,000 and then the element. Undefined function, oops, I'm missing a db here, it's my bad. Okay, so we got our list, length of db is 5, yeah, okay, I got the inclusive range here. But anyways, we got our 500,000 elements more or less. And now let's just try to use timer tc to measure this. Again, not very scientifically, but it's gonna be fine for us. So protohackers.prices server.db.query db from 0 to 100. Let's do like 1 billion, which should return all the elements, I think. So this takes 24,000 microseconds, so 25 milliseconds for querying all the elements. If I query just like a few elements or like a smaller set, it still gives me 25 milliseconds more or less. If I query one element, it's 10 milliseconds. So like all the times are really reasonable for our use case, where anyways the network is also gonna take a bunch of round trip times for the round trip, so I'm not really worried about this. This data structure is totally fine. We could optimize. We could stop if we sorted the list. We could kind of find the beginning of the range and then just get elements until the end of the range and throw away all the rest of the elements, which would be more efficient. But the insertion would be more expensive to insert in a sorted list, right? To keep the list sorted. So not really worried about this too much in this case. Okay, so we got our data structure. Let's go for our binary protocol. So I go back to the prices server here. The problem description says that every message is 9 bytes. So the first thing we can do is get 9 bytes at a time so it's the first time that we're going to use something different than 0 in gentcp.receive. So also one thing that I want to do before moving on is I want to alias protohackers.prices server.db. So we have this available. And so here, instead of saying receive until closed, which is what we had in the Echo server, I'm just going to rename these to handle requests, which is going to be our recursive function. This function doesn't take any of these anymore. and I'm also gonna pass the DB. So we'll keep recursing on this DB data structure so that we have some sort of state in this thing. Oops, sorry, this is just called DB. Right, okay, so this is looking good, except that this is gonna return okay. So when we're done handling requests, if there's an error, we just close. Okay, and now let's go write this handle request function. We don't need the limit anymore. And what we're gonna do is we're gonna listen for 9 bytes, right? So if we get, let's just get rid of these two. If we get okay data, we know that data should be 9 bytes or less. So let's just do when byte size data equals 9. So in this case, we can handle the single request. So let's pretend we have a handle request function, takes the data, takes the DP, and if it returns a response, then we can send a response. But for insert request, we don't want to send a response. So let's just pretend that this function is going to return nil and an updated DP. And if that's the case, then it means that there's no response. So we'll just recurse over the socket and the new DP. If it returns a response and the DP, then we can send the response back, gentcp.send. This is socket and response. And then we again keep recursing, socket DP. And if it returns an error for some reason, like a malformed request or something, we say error invalid request. Okay, then if we get an interesting case here, what if we get a timeout? So we don't get the 9 bytes within our time. Well, it just could be that the client is sitting idle. So in this case, we just want to handle this specific error and just call this again. So give a chance to the client to just kind of keep going. We could increase the timeout to reduce the number of times we get into this. If we get closed, it means okay. If we get a reason, we bubble it up. Okay, so now let's write the handle request function. So once again, pattern matching here really makes matching on the messages really, really nice. So if you've never seen binary pattern matching in Elixir and Erlang, it might look a bit foreign, but it's just the absolute best. So we can just match by saying, okay, if a request starts with the byte identified by the capital I character, so this question mark I just turns into, I can show you like IEX, it turns in an integer. It's just a sort of like replaced by the Elixir compiler with an integer representing the ASCII code, the ASCII byte representation of this. So easy peasy. And if we get then a timestamp, which is a 32-bit signed integer, big endian, as per the problem description, and then we get a price, which is again a 32-bit signed big endian integer. This is a well-formed request. So in this case, we don't return a response, but we add, oh, and also this takes the DB, data and DB. So the second argument here is the DB. And we add the timestamp and the price. Okay, if we get a request that starts with Q instead, and then there's a mean time, as the protocol called it, which is again the same kind of integer, and then a max time, which is once again the same kind of integer, and then the DP. Then in this case, the average we can calculate it by doing db.query with mean time and max time, and we return the response is going to be the average encoded again as a 32 signed big integer, and then the DB. Okay, whatever else we get here, handle request other DB, we return an error. And now that I'm thinking about it, this actually allows us to not really check when byte size equals 9 here, because if the byte size is less, we're going to handle a request that's less than 9 bytes. Just gonna error out, which should be fine for our case. Okay, so let's maybe write a test for this. I'm gonna create proto-hackers prices server test .exs. All right, and I'm gonna say the module proto-hackers.prices server test. use xunit.case, and we say test handles queries, something like this. And we're gonna do our usual thing that now we should be used to, which is I'll spin up a TCP socket that connects to the server that we're running. Mode binary to talk in binary protocol. Active false as well. Great. And then what are we gonna do? We're gonna send a bunch of queries. So I'm gonna do gen tcp.send on the socket, and I'm just gonna write the manual protocol by hand here. It's not too hard. So timestamp 1032 signed big, and the price is gonna be 132 signed big. So this is a well-formed query, I hope. And then I'm gonna do the same thing, but I'm gonna say 2000 here and 3000, and then I'm gonna say 2 and 3 here. Great. Now I'm gonna query this. So I'm gonna say gen tcp.send socket, and the message is gonna be capital Q. The min time is gonna be 32 signed big, 1000. The timestamp is gonna be 1000, and the end timestamp is gonna be 3000. Okay, and now if I receive gen tcp.receive socket 4 bytes, because we know that the integer is 4 bytes, and 10,000 here, and let's assert that this is equal to okay, and the average should be 2, still encoded at 32 signed big. Okay, let's try to run tests, and they pass. That's great. One test I'd like to have in here is that prices are stored and averaged per client. So I'm gonna just add a test for that. I'm gonna say test handles clients separately. Okay, I'm gonna copy this here and start 2 sockets. I'm gonna say socket 1 and socket 2. Then I'll copy these over, and let's say that we store 1000 on socket 1, and then we store 2000 on socket 2 over here, and then I copy this querying thing, and I say, okay, if I query socket 1 from let's say from 1000 to 3000, that's fine. Then I should get 1 as a response, and if I copy this and query socket 2 from 1 to 3000, I should get the average of 2. Let's try this out. Oh, and define function socket, sorry, I missed it here. 1 and 2. Okay, my bad. Okay, so this passes. Fantastic. So today was pretty easy. That's pretty much it. That's our server. So let's open up our 5003 port on fly.io in our deploys here. Just gonna copy the configuration for our previous problem, and I'm gonna move the port to 5003. This looks good, and let's deploy it, and I will see you when this finishes deploying. Okay, so I finished deploying. I will just get the IP, the public IP for this, and let's go put this in ProtoHackers. Okay, right on. We are in the problem description. I will just paste the IP address here, and I'll put the port, and let's check. All right, seems like the first checks are passing 200,000 prices in random order. So yeah, it looks like our tests are passing. Okay, that's awesome. So today's puzzle was pretty easy. I'm convinced a big part of that is how easy it is in Elixir and Erlang to deal with binary protocols through pattern matching. I always loved that, and I've written my fair share of binary protocols like Cassandra's binary protocol, HTTP2, and more. So I'm a big fan, definitely. Cool. Well, thank you for watching, and I'll see you in the next video.